Oh, by the way, the recording for the invited, like last guest lecture from IBM, I send it to IBM for review. And if they approve it, I will be able to share it with you. If they don't, then it's gone, okay? And I was told that this approval might take a couple of weeks at least. There are a few other folks who requested for the recording who missed the session. So in case you were wondering. All right, so in the resistive random access memory section, we first discussed the high-level IV current voltage characteristics. We talked about the hysteretic nature. We talked about how you can program this material from high resistance state to low resistance state and back to low resistance state again by using two different polarities. Okay, we talked about a problem of forming, and I told you that this will be one of the showstoppers, and I haven't even given you the reason why. I just told you that it's the problem. Yes, you just have to do it once in the lifetime of this device, but then even then it's a problem. And in today's lecture, we'll cover that. We talked about some physical reasons why this type of resistance transition occurs. One example was a situation where, oh, by the way, the structure was metal, and some sort of oxide or insulator, separating these two metals. And in some cases, metal atoms can form a filament by diffusing through the oxide. That's one type of memristor. Okay. The other kind was, yes, the metals are there, but they don't move around. You create vacancy in oxygen, and they can form a filament. So instead of using the metals as active element, you use the oxygen inside the oxide as an active element. But the process is essentially the same. You create a filament, there you go. And there are, we talked about different physical mechanisms through which electrons can flow from one point to the other. It's not just one kind of tunneling. When you see metal and insulator, and you have current flowing through this device, the first thing that should come to your mind is tunneling. So yes, there is a lot of tunneling involved, but that's not the only mechanism. There are other mechanisms, including hopping and so on, involved in this process. Okay, and then finally, the third kind was you don't have any filament at all. You have redox reaction closer to the interface right here. So if you have more reaction, you create a thicker layer or thinner layer. So you can have different thicknesses of the layer, and based on it, you can have different levels of resistances, possibly being used to have multi-bit memory, right? That's where we stopped in the last class. So we start here today from the array architecture. It's making my life easy. You know why? Just take a look at the structure. Can anybody tell me what this device is? It could be, can it be a magnetic tunnel junction? Can it be a phase change memory, PCM? Can it be a resistive RAM or memristor? Basically, let me just use memristor. Some people prefer to call this overall structure resistive RAM, not just the entity itself. They prefer calling it memristor, and overall memristor and transistor combination is a resistive RAM. Some people prefer it that way, okay? So anyways, you see that their structure is exactly the same. We have a resistive element and we have a selector, a transistor that allows us to access it, or access device. So I don't have to do anything. This is a repeat of what we discussed before. The array structure remains the same exactly as the STT MRAM structure. Does that make sense? You have word line, you have bit line, and you have source line, similar to what we have before. All I had to do is change the animation and make it memristor. That's all. Okay, one more thing that I haven't really talked about much, which I will briefly talk about either now or later. Maybe I can just mention that briefly since it's there. Have you mentioned that there is a parameter called sneak path? And sneak path, basically I meant to write sneak path current, but in short, we just mention it as sneak paths. What does that mean? And notice there are two array structures that I'm showing you. And we discussed both, by the way. On your left, it's the most common structure. You have a transistor as an access device. Whenever you want to read or write into a cell, you turn on the transistor and you turn off the rest, turn off everything else so that they don't get disturbed. Simple concept, okay? But then there was an argument that this transistor takes up more area than the memory element itself. So we decided to get rid of the transistor. And I told you that we use some sort of selector. But I didn't talk too much about the selector. I talked about the crossbind memory. Remember V/2 biasing? Did I talk about V over 2 biasing ever? Let me remind you one more time. So there are 4 cells. Maybe you want to access this one. Okay, let me just increase the number of cells a little bit more. That way it will probably be more meaningful. Okay, so you want to access the green one. So what you do is you apply full voltage V and 0 across the cell. So that means this cell gets V across it, the full voltage, read or write, whatever, access voltage. Now, problem is these other cells will also get V unless you do what? Unless you do V over 2. And remember, I mean, just reminding you, I definitely covered it. Did I talk about insulator metal transition materials? There was a threshold. This was critical current for insulator metal transition. And I told you that V will be here and V over 2 will be here. That means with V over 2, this material will be insulator. With V, this material will be metal. Ringing any bell now? Okay. So if we do this type of a biasing, notice these cells, what is the voltage across these 4 cells? Absolutely 0. So they are called unaccessed cell because they are not in the same row or same column as the access cell. They are called just unaccessed. Done. These cells, which are in the same row as the access cell, are called half access row. Why half? Because notice the voltage across them is V over 2. If you think about it, V and V over 2. So that's why half access row. And these are called HAC, half access column cell, which share the same column as the access cell. Okay, you see the point? All right. So, basically, this is the cross point architecture. So what you see here is the selector that we talked about before. So this architecture applies to memristive array, STT MRAM, not STT MRAM, sorry, magnetic tunnel junction based array, because when you remove the transistor, it's no longer STT MRAM. It's just a magnetic tunnel junction with a selector. Okay. So the same argument. And what do I mean by sneak path? Basically, even if you have 0, when you have exactly 0 volt across a cell, you have 0 current flowing through them. But when you have something, even if you have V over 2 biasing, it's not 0, right? You see the point? Let me point out one of the cells. Let me draw it here. So this is the cell which has V over 2 across it. So that means there is a non-zero voltage. And the resistance that it has is the insulator state resistance and the resistance of the memory. Right? There is a finite resistance. So when you apply a voltage to, no matter how high the resistance is, even if it is a 1 giga ohm, I don't care. If you apply some voltage to it, say 1 volt, wouldn't there be any current? There will be something. The current will be negligible, I assume, but still there will be something. This current is called sneak path current. So this will sneak in no matter what you do. Yes, it will not disrupt the memory. That's what we are worried about. But there will be some sneak path current. And that's what we mean by that. These are sneak paths. Okay. So notice when you have access cell, you have sneak path currents through the other cells, some current. And these currents create some challenges for sense amplifiers, which I haven't talked about yet, but we will talk about later on. Okay. When we discuss the peripherals, I'll get back to this slide again. But I'm just trying to clarify any confusion if you had any with sneak paths. Okay. So this is just the 3D structure of what I drew here, a fancier version of the same structure that I drew. Okay. All right, and notice the names here: unaccessed, half-access column, half-access row. All right. This is just taken from a reference which shows that this array works. Basically, you write and read. There is nothing new here. Let me just guide you through how to read this. Okay, this is research paper, so they don't care about teaching. They just care about getting the message across. But let me help you with the easy reading of this paper, figure. But please pay attention. It's a busy figure. Look at write 1, write 0. So in this section, we're just going to see write operations. So how do you write? Before you read or write, you turn on the word line first. Do you guys all agree with it? So notice WL is the word line, and you're writing the word line. I mean, I'm just showing you how to read a busy figure. First read, write 1 operation in M22. What is M22? It represents memory at second row, second column. Okay, so second row, second column. Notice it has been highlighted as well. So this is being read or written. This is being written. Okay, so before you read, what do? You turn on the word line. Which word line should you see? WL2. So that's why it's plotting WL2. Okay, so WL2 goes high. That means it has been activated. So whatever action occurs will occur within this zone, not before, not after. You guys all agree? Okay. And then after you turn on the word line, all you do is you let us access, not this one, access this cell. But then you have to apply a voltage to switch, right? You see the point? You have to apply a voltage across this device to switch it. So there has to be a voltage between the bit line and the source line. Do you guys all agree? And source line could be ground. So you have to apply a voltage to the bit line. So notice this is the voltage you apply to the bit line. Are you guys all with me so far? Quickly going back to the IV again, just to point out. Notice when you write 1, let's call it set. If you have positive voltage, when you reset, you have negative voltage. Do you guys all agree with it? But the voltage will be applied across the device, plus minus or minus plus. Okay, so now go back to this figure again. When you write 1, you apply some bitline voltage. When you write 0, you apply the opposite polarity of bitline voltage. Notice that this is 0. So you can read. And the level of bitline voltage will be determined by the IV of the memristor that you're using, depending on the set voltage and the reset voltage level, right? Okay. All right. So what do you see here? How do you know that it was written well, right? Notice this is plotting the resistance of the 2 cell resistance. So resistance was high before, now it is going low. Do you see that? And at the same time, there is another way to see it. You don't see the resistance changing. You have to, this is a secondary measurement. You have to look at the current and voltage and then back calculate resistance. But you can directly see the current using an ammeter. And you see the source line current, the current that comes out of this line, look at the blue line. It goes from low to high. Current going high, meaning resistance reducing. You guys all agree with it? Okay. And by the way, it's a busy figure because this plot belongs to the left y-axis, this plot belongs to the right y-axis. So they're plotting different things, current and resistance here. Are you guys all with me? I mean, I could have just brushed it up, but I thought that let's dive in and see how to read these figures. So if you can read this, you can read the other one. Notice now the resistance going from low to high, quite the opposite. All right. One more thing that I want to point out. Yes, the resistance, folks, resistance goes low or goes high and stays that way, even after you change the word line. That is the signature of non-volatility. So we don't care what the biasing is. Once you program me to low or high resistance, I'll stay there. That's the whole point about non-volatility. But what stops after you turn off the word line? Check out this current. Well, the current changes when you have a switching in the resistance, but then current goes back to 0 once you turn off the word line because the transistor shuts off the current. And notice there is a current here as well, but the current goes back to 0 after you shut off the word line. So when you read, this is not reading, this is writing. But when you read, you have to sense the current levels, right? Now you're not sensing, you'll be sensing here. Notice, this is current level, this is another current level. For one of them, the current level is low, the other one is high. But when you have to read, you will have to activate your sense amplifier to feed this sense source line current in, okay? And you have to make sure your sense amplifier activates within this zone, as long as the word line is on. If the word line shuts off, you have nothing else to sense. Are you guys all good? So what do we sense? We sense the current levels. Okay, does that make sense? During read, you still turn on the word line. Notice WL2 is the word line. You still turn on the word line and you apply some voltage to the bit line. Notice one more thing very carefully, folks. Compare this bit line voltage with this one. You have applied a small amount of voltage so that it doesn't switch. It just creates some current. And you want to see whether this current is high or low. Depending on what the resistance was, it could be high or low. That's exactly what we were looking for. Make sense? Any questions? When you go back home, try to read it by yourself. I know it's really busy. I deliberately use this basically because you have to get used to this type of visualization. That's exactly what you will get in real life. Okay. All right. Few quick, I'm not going to through this laundry list. These are for your information in case you have any interest there. I wanted to show you the diversity in the type of memristors that we have. It's not just one device. There are so many different oxides and other device combinations that gives rise to memristive properties. And notice the switching mechanism is different. There are different reasons for which they switch. And people experimented and figured that out, okay? On-off ratio. Notice the on-off ratio goes from 20 or 10 to 10 raised to 7, right? There's a huge spectrum. So somebody just notice, I discovered a memristor which gives you on-off ratio of 10, sure? And somebody else coming up with 10 raised to 7, kicking you out of the park, right? So apparently there is a whole spectrum available to us. So obviously there is no point going through the numbers, but just take a look at the diversity, okay? And you also know the type of materials that act as memristors, for example. All right, moving to the problem with forming. This slide will tell you the problem with forming, okay? So notice, this is a memristor, and this is a transistor, 1T, 1R. This is what I've been showing you so far in the array structure and whatnot. But that's not really true. For memristors, you have a problem. You have to form the memristor before you use it. It's kind of like initializing it's before using, okay? So how do you do that? Do you remember that forming requires a higher voltage, much higher voltage than set? So the regular transistor that we have with the memristor cannot handle that high of a voltage because they are tiny, okay? For high voltage transistors, you need bigger transistors. Are you guys all with me so far? So we typically use a dedicated transistor for forming. It's kind of like used for forming only once in their lifetime, that's all, okay? So that's a huge waste if you think about it. And notice, this is the memristor's dimension. This is a realistic diagram taken from one of our own paper, okay? 80 nanometer, for example, 80 nanometer. And this is an huge transistor sitting there just to make sure we can form. Because if the transistor is not big, it will not be able to handle higher voltage. Okay, so you have this huge transistor to make sure you can form it. You might be wondering, why don't you form it separately? Then will you make it by hand? Like billions of memristors, will you make it by hand? No, it has to be formed on chip. Once you have the chip, you initialize it and you use these forming transistors, which are really big and bulky. Does that make sense, folks? Okay, what does this other figure show you? It shows you that this is 3 volt forming voltage. Notice 3 volt. These are real data from our experiments with Professor Rose. Okay, Professor Rose and I, we worked on a project where we had these numbers exactly. So 3 volt was the forming voltage for a memristor, and then this is 1 volt. So improvement on memristor characteristics, and that led to this huge transistor being tiny. Obviously, at least 1/3 reduction, if not more. So if you could reduce this forming voltage, that's another research direction that material scientists are looking at. Can you have forming free memristors? That's all with me so far. If you Google it, you'll find, yes, forming free memristor. They're there. But then I told you there is no free lunch. They come at a cost. There are some other issues for which you cannot really use them as of yet. So we have to live with forming as of now. So that is the biggest challenge with with memristive memory, because you need forming.
So do you need a forming transistor for every single cell?
Yes.
No
yes and no.
Like columns or anything like
exactly. So yes and no. That's what I was saying. So apparently, in some circuits, like for example, these are also used in oscillators and neurons and synapses. Okay, then you need dedicated. But in memory arrays, we often share these big forming transistors across the row or across the column. Okay, we have tried to do so, but there are some other challenges. Remember, when you share a transistor, they take the load of all these memristors. So it has to be huge. So there is a trade-off. Will you have like a huge transistor, or will you have like 5 small, medium-sized transistors? So there is a design optimization challenge there as well. So it's not ideal, honestly. Nobody likes it, but we have to live with it. Okay. All right. I already spoke about this slide slightly. Remember, silver, hafnium, platinum. Did I come to this slide in the last class? Remember, just to show you how silver atoms diffuse through the oxide and create a filament like this, and then you can break the filament to make it high resistance state as well. But when you break it, it no longer goes back to the silver electrode all the way. It just creates a blank space like this, only a blank space. And then once you provide enough voltage, it creates the bridge back on. So that's why set and reset are quicker and requires less energy, but forming takes a lot of energy, because you have to start from pristine condition, bring all these atoms here. So that takes a lot of energy. All right, now this slide is supposed to tell you something else, not just this forming process. It's supposed to tell you that there is a difference in the hysteresis. What is hysteresis? This, cyclic IV that you saw, we just call it hysteresis. Okay, and there is a difference in hysteresis that we observe in certain memristors. Notice this one, cobalt, hafnia, platinum. We notice that in this device, when you create a bridge, even when you remove the voltage, make it 0, it basically sustains the bridge. The bridge doesn't get broken automatically. Okay, so basically the IV looks like this, which is a memristor, a non-volatile memristor, which I showed you before. This is the device we have been talking about so far. But silver, hafnium, platinum basically just change a metal, for example. It gives you a different scenario. The filament that it forms is flimsy. So basically, as long as you have voltage applied, it has a filament and it keeps conducting. But if you remove the voltage, it goes back to broken filament again automatically. The filament can never survive without an external voltage being there. So it's not a memory, it's a volatile memristor. It forgets what it was programmed in. So in terms of IV, for non-volatile case, things look like this. You switch from high to low resistance state, and then when you make it 0, it gets stuck here. But for volatile, you switch from high to low resistance state, but if you go back to 0, basically it goes back to insulating state again. Every time you start, it always starts from the insulating state. The moment you restart, it always follows this line. So that's the difference. Okay, it's not a memory. This is a memory. Okay, but towards the end of this course, I will show you some ideas which brings together the power of volatile and non-volatile memristors in one unified memory to enhance the performance of many memories. Okay, does that make sense? These devices, the ones that show you volatile memristive characteristics, they are called threshold switches. Threshold switches, and I'll tell you more about them. Okay, so don't worry. I'm just brushing up on this concept at this point. So they cannot be used as a memory, as you can imagine, but they can be used as something else. They could help other memories. And since we are here on the topic, I want to quickly highlight these volatile memristors are really great candidate for this selector. They're used as selectors. Okay, I didn't tell you when I first introduced cross-point memory, what do we use as selectors? Basically, we use these volatile memristors as selectors. As simple as that. Are you guys all good? Okay. And I'll talk more about it. I have a dedicated lecture where I'll dive deeper into these devices and talk about it. All right. I have another slide, which I just drew it already, but I wanted to show you non-volatile versus volatile memristor. The difference is for one of them, once you switch and go back to 0, it doesn't lose its memory. If you restart, it will follow the path that it was in before, not the default insulating path. Okay, but this one, if you program it to low resistance state and then remove the voltage, it will go back to 0, like high resistance state. And next time when you turn on the device, it will follow this insulating line again. That's the difference. It's like, I don't remember anything. It's funny that we even call it a memristor because it doesn't have a memory. So that's why volatile memristor. And that's why people prefer the term threshold switches instead of volatile memristor. That's what people prefer more. Okay. And I already used the term, did I not? Insulator metal transition, VCIMT. See, all of these apply to this material. And if you take a step back, I mean, don't look at this busy slide, maybe. Let me draw it for you. So you have insulator to metal transition here at this point. And then metal to insulator transition occurs at a different point, MIT. So you have two critical points, insulator to metal transition, metal to insulator transition. Notice both transitions occur within the same polarity. You don't have to go to the other polarity. Does that make sense, folks? You see the uniqueness here? For this memristor, once you switch to low resistance state, you can never switch it back to high resistance state as long as you don't change the polarity. See the point here? You have to go and apply a voltage on the other polarity so that it goes back to high resistance state. But not for this one. All you have to do is reduce your voltage below a critical level. So you have to maintain a voltage above a certain level to keep it metallic. Otherwise, it will just give up. It will go back to insulating every time within the same polarity. So question, what happens when I have used opposite polarity? It basically behaves identical like this, like a mirror image. Am I confusing you too much? These are all new stuff, I know. So you will need some time to digest. But what's important is not to get everything here right now, but to get everything after you go back home and read through it. And if you are confused, please don't let it be. These are critical stuff that you have to know about. Folks, if you see where technology is going, right? Like literally people are dealing with crazy, small, tiny quantum mechanical stuff. So these are necessary for you to understand. You cannot just, okay, I mean, it's not for me. It's for you, actually. There is no one else who could understand if you don't, okay? You can understand it. So don't let me go so easily. Please use my office hours. If you're still confused, come talk to me. I personally work on these things for a living, for example, right? So I hope that I can definitely help you. Yes, Michael.
So for the volatile memristor, can you go back to the
Yeah, of course.
so you're just leveraging the right side. So like
Exactly. Yes, absolutely. So this guy, this volatile memristor, doesn't have any storage capability. All it does, it just behaves as a switch. And I'll show you, don't worry. Like I said, I will dive deeper into how we can use it as a switch. I'll talk about those details in a dedicated lecture. That's why I'm just introducing them, making you aware of the difference between volatile and non-volatile, and then moving along. But we have a dedicated lecture where I'll show you exactly how we utilize their characteristics, okay? All right. Okay, so examples. I just wanted to show you some examples, some real examples. I always like to use real examples so that you know it's not just one device somewhere in the corner of the world, right? There are so many of them. Notice, you don't have to go through the copper doped hafnia, vanadium, blah, blah, blah. Don't worry about the name. Just look at the IV. As an engineer, you look up the macroscopic characteristics. What are the signatures here? You have IMT and you have MIT. Notice MIT occurs before you go to 0. Do you see that? This is another material. You have IMT, insulator metal transition, and then metal insulator transition before you go to 0, and so on. Some have narrow hysteresis, some have wide hysteresis, some have really high on-off ratio, some will have really low on-off ratio, but there is a spectrum out there. Okay, and the reason for this type of transition is different, and few reasons I mean could be correlated electrons, which is often observed in vanadium oxide. Vanadium oxide is an interesting compound. Notice it's just a compound. It's not a structure like this one. Silver, hafnia, platinum is a structure. It's not a compound, is it? It's not a compound. It's a structure. Silver, hafnia, platinum. So there is filament formation, all those stuff. But vanadium oxide is just a compound which shows you this type of characteristics. And why? This is unique, by the way, and there are at least several thousands of papers written on vanadium oxide, their usage and why they do what they do. Just imagine that. Just Google vanadium oxide, you see like so many different things. They're used, their property, this type of transitioning property is used all the way from glass that switches from transparent to opaque by pushing a button. You must have seen in some airplanes, they use it in some airplanes as well. To electronics, okay, to oscillators, even spiking neuron for neuromorphic computing systems. Just imagine how prevalent these devices are. Okay, all right. This is actually the final slide of today's lecture, and I want to show you, I want to leave you with this because we will get back to it towards the end of this course. One more important point about these volatile, sorry, volatile memristors. This will actually be volatile memristors. Sorry, I will correct this slide. Okay, this should be volatile memristors. Vanadium oxide is a volatile memristor. Okay, so what are the signatures? The signature is the transitions that you get. They are abrupt. They're abrupt. So this is something that we like. One other thing is you get high on-off ratio, not just 10x. Notice this is 10 raised to minus 16 to 10 raised to 0, 6 orders of magnitude. Huge on-off ratio. So you get really high on-off ratio in these devices. All right. Compare that to a hafnium oxide based memristor that only gives you like 20x to 100x max. Not much. Okay. And hysteresis, basically you see that hysteresis here. These three are the signature of these devices that we utilize in circuit design quite a lot. Okay, and this slide tells you one more additional information, which is there is a critical temperature associated with these devices. What does that mean? Below this critical temperature, it demonstrates this type of hysteretic switching. But if you exceed that critical temperature, it no longer shows this type of transition. It just behaves like a metal. Does that make sense to you? It's like magnets have their Curie temperature. You know that? If you increase the temperature beyond the temperature, it loses its magnetism. Right? Similar to that. So it has a critical temperature. Some material have 600 Kelvin, some has 100 Kelvin, some has 200 Kelvin. So you have to be mindful of the critical temperature of the device as well. Because if it is lower than 100K or 200K or 300K, that means you need cryogenic. Right? 300K is room temperature, as you see. So if it is above 300K, that's when it is usable for electronic circuits at room temperature. Ideally, we prefer to use above 400K because 400K is considered to be the chip operating temperature. When the chips work, they heat up eventually. So they go easily above 400K. So we should look at devices and materials that are above 400K. All right. Anyways, so I just wanted to make you aware of this concept because they are related, and then we are done with this lecture as well. Okay. Thank you. I will post a recording for the phase change memory, the remainder of the phase change memory, which is a tiny fraction of the overall lecture. And I'll post an announcement on Canvas with the overall syllabus for the midterm. Okay. Prepare well. I'm available to answer questions, and I'll be just an email away. Okay. Thank you.